Welcome to this session. This session will give another example on how to determine Jacobian functions. So we have two functions, x and y, which depends on theta and omega. And we have to show that the Jacobian of x, y with respect to theta and omega, when x and y are as defined in this problem, is given by a squared over 2 hyperbolic cosine of 2 theta minus cosine of 2 omega. So as I told you from the start of the topic of Jacobians, the topics assumes that you are well grounded on functions and partial differentiation and also determinants. So please, if you still have some problems, I advise you to check those topics in calculus and linear algebra before you come solve problems on this chapter. Okay, so solution. By definition, the Jacobian of x, y with respect to omega, theta and omega is the determinant partial x, partial theta, partial x, partial omega, partial y, partial theta, partial y, partial omega. This by definition. And then partial x, partial theta, when you differentiate a hyperbolic cosine function, you get a positive hyperbolic sine function. So therefore, this will give us a hyperbolic sine of theta times cosine of omega. And then partial x, partial omega, when you differentiate a cos function, you get a negative sign. So this will be negative a hyperbolic cosine of theta and then sine of omega. And then this one, you differentiate y with respect to theta, differentiating hyperbolic sine, you get hyperbolic cosine. So we'll have a hyperbolic cosine of theta sine omega. Differentiate sine function, you get cos function. So this will be a hyperbolic sine of theta cosine of omega. Now these are 2 by 2 determinants, so simply partial x, y, partial theta, omega will be a, now this time, this one will have hyperbolic sine squared theta, and then normal cosine squared omega, minus will be plus a, this would be hyperbolic cosine squared theta sine squared omega. That's what you get. And don't forget these two identities from calculus, that hyperbolic cosine squared of an angle A or a number A minus hyperbolic sine squared of the same value, we get 1, and cos squared A plus sine squared A is 1. So from this, you know that hyperbolic cosine squared A can now be written as 1 plus hyperbolic sine squared A, and hyperbolic normal cosine squared A can be written as 1 minus cos squared A. So now from this one, we write the Jacobian of xy with respect to theta omega will be A. Now this, we write just hyperbolic sine squared theta, and then instead of writing cos, we write it as 1 minus sine squared omega, and then plus this one, we write it as 1 plus hyperbolic sine squared theta, and then we multiply by sine squared omega. So I remember this a times a, this was supposed to be square, this also supposed to be square. So correct that. So this will be squared, and then we have an a squared here. So from which you have this Jacobian will be factor out a squared. So hyperbolic sine squared theta minus hyperbolic sine squared theta sine squared omega plus I have factored out a squared sine squared omega plus hyperbolic sine squared theta sine squared omega. Now, let's see this bracket, this term here, and this term here are the same, but of different signs. So therefore, this and this cancels out, so that we have the Jacobian of xy with respect to theta omega will be a squared into hyperbolic sine squared of theta plus sine squared omega. So then now we can derive this one as, so we want to work smart with the expression we have so that we prove the result given on the right-hand side from the question. So we can write this one as a squared into hyperbolic sine squared of theta, and then minus 1, or really not minus 1. So even this, we use also from calculus, we know that hyperbolic sine squared of A is the same as hyperbolic cosine of 2A and then minus 1, and also sine squared of A is the same as cos 2A minus 1. Or really, so let's just say, so cos of A plus A is cosine of, just for this one, cosine of A, cosine of A minus sine of A, sine of A. So this cos squared A minus sine squared A equals to cos 2A. So which can be written as 1 minus sine so which means cos 2A is the same as cos squared A minus sine squared A, and this can be written as 1, this is the same as, so remember this over 2. So we can write this one as 1 minus sine squared A minus sine squared A. So which will be the same as 1 minus 2 sine squared A equals to cos 2a. So this identity should be now, which with 2 sines squared a equals to 1 minus cos 2a, and then you divide through by 2, divide through by 2. So this should be 1 minus cos 2a divided by 2. So these are the identities that we're going to use to rewrite our expressions. So from these two relationships, so you say, since hyperbolic sine squared of theta is the same as hyperbolic cosine of 2 theta minus 1 over 2. And from what you've shown here, sine squared omega will be given by 1 minus cos 2 omega divided by 2. Then this Jacobian will be partial x, y, partial theta omega equals to now a squared. But because each one has a 2, I can factor out that 2. And then for this part, I write cos a hyperbolic cosine of 2 theta minus 1. And this other part I have plus 1 minus hyperbolic cosine, hyperbolic cos of 2 omega. And minus 1 plus 1 is 0. So this implies the Jacobian of xy with respect to theta omega will be a squared over 2 into hyperbolic cosine of 2 theta minus normal cosine of 2 omega. And that proves the result. So that's how we show that problem. Thank you.